Feel free to ask any questions as we go along. Just raise your hands. There's a pretty bright light up there. If I don't see you, just kind of wave around. I'm happy to take them. We should have some room at the end for Q&A as well. Slides will be published on SlideShare. There's lots of little links and source material on the bottom. So if you want to dig a little deeper later, absolutely. And I'm pretty sure that Serge puts them up online as well. So keeping it real time. They actually Serge guys suggested I spruce up the title a little bit. And so in your materials, I think it says the Metamorphosis of real-time queuing or something like that. And it looked like a really good title till I started looking for the pictures to go with the title. And so this kind of comes up. I'm Dutch, so I didn't put together Metamorphosis to a Die Verwandlung. And that's the picture of Franz Kafka doing the work. And I didn't want to use that picture in case you thought this is what happened to me as soon as you started doing Kafka stuff. So I just stuck with the fancy race car. I figured that'd be OK. All right, so a bit about my past life. I ran the engineering team behind the RIPE database. You know them here as Aaron. If you ever got any IP addresses, you're on the internet. You're welcome. And then the team behind Ubuntu Server at Canonical. And we did the very first cloud releases there for Lucid and Trusty. And as the kind introduction just mentioned, you may recognize me from such previous talks as how to measure everything or architecting in AWS for resilience and cost. It is tradition that there's going to be an AWS outage while I talk. So if halfway through you all get your pagers and need to walk out, then that's just karmic justice right there. 5 years ago, I joined a company called Crux. And you can think of it as kind of Google Analytics for audience rather than traffic. Or if you want the thing that Netflix does to figure out what you want to watch, and that Amazon does to figure out what you want to buy, we do that for everybody else. And that's for any type of content you want to consume. So here's kind of a list of our customers. And it turns out that this type of thing, this personalization, this analytics thing, is pretty common for just about anybody with any digital property. And it includes some of the top 50 websites that you use. We have a very strong slant on data privacy as well. We believe it's your data. And if you go to the New York Times, it's between you and the New York Times. You don't sell that stuff and so on. And that was really attractive in Europe back in the day already. When they started with data protection, we see it all over the world. So lots of stuff that we have to do, lots of stuff that we have to do in real time, and so we get lots and lots of traffic. Every time that one of those websites gets a request, we get one too, at least one, sometimes more, and we get them from all over the world. It means we're on the critical path for delivery for a lot of those websites, and that means that outages would be pretty bad. We run our entire infrastructure inside of AWS, so we all know what can happen there. And like I said, I expect an outage to happen again today. Maybe we got lucky, we got a little earlier than the one on Sunday, but if your pagers goes off, that'll be cool. So to kind of give you an idea of what we do and then put a little bit of context around those numbers, I'll start with saying it's a bit of an apples and orange comparison because Twitter does do a little bit more work on their incoming tweets than we do on incoming data. But Twitter's about at 9,000 tweets per second on average. I think the current record is during Castle in the Sky that was aired in 2013, where everybody in Japan tweeted the same word at the same time as it happened in the movie. And that was at 144,000 tweets per second. And that peak is roughly our average. So to show that we have a bit of reach, we're about 5 times Wikipedia, at about 2.5 billion users we see every month. And we continue to process the analytics for each of those users. Some of that stuff is in batch, but a lot of it is in real time. And that's what this talk is going to be about. Like I mentioned, we run all of our stuff in AWS. So all the stuff here will work for data centers, but it's battle tested in AWS as well. So including all the funky network stuff you'll encounter there. All right, let's get to it. I'll start with a disclaimer. As you'll see in our use cases, we can afford to lose a message here and there or get one delivered twice. If what you do is in healthcare and your app administers morphine to patients, this might not apply to you. If it invests your life savings, again, these recommendations may not apply to you. All right, on to the use cases. We have 3 main ones. Discovery, which means searching through any type of data that we gather from our systems, applications, logs, and so on, so we can go and look for them and find patterns. A lot of processing, which basically just means real-time streams. We have predefined sets of rules and logic that we want to apply. We do some transformations. We update storage systems. We serve out of those storage systems. And the last one is statistics. It just means insights into trends. So we're going to try to solve, with our queuing system, all 3 of those. A little bit more about discovery. We have lots of system logs, as I'm sure you do as well, the stuff that is produced usually through syslog and other things. Also, our applications log a lot, especially if something doesn't quite happen the way it was anticipated. it took longer. That data format wasn't the way we expected to. That thing wasn't quite working. Compared to everything else, it's pretty low volume, but it's really high signal. And we want a really long retention. Like these look-back windows, these analytics are pretty important. For processing, it's almost the other way around. We take all these end-user events as they stream in, and we apply rules and algorithms, and then we update our data stores. The volume is really high. I was showing you before, it's like 150, 200,000 messages a second that we pump through that stuff. Very high signal, but we don't need to keep it for very long in this queuing system because at some point batch will catch up, right? You know, if you do a daily or a weekly job, it's fine. But you want to update as fast as you can. And the last one is statistics. You just want to track the occurrence or the value of a certain thing and then send them into an analytics engine. It might be as simple as which parts of the website or which publishers or customers are very popular, what are the response times doing, and so on and so forth. As you mentioned in the intro, I did a whole talk on how to gather millions of metrics. If that's a thing that you're interested in, you can scale Graphite up to the wazoo. And I think we have a few vendors here in the back that will sell you really cool metric stores for a reasonable price, I believe. Can I speak up a little bit? Sure.
Yes, please.
First off, there is no, sorry? Okay. All right. There's no one-size-fits-all solution. So you are going to have to choose some constraints, unfortunately. So pick them carefully. Make sure they fit your use case, and in the end, embrace them. You're going to be locked into whatever constraints you adopt, so you might as well just hug them and don't look back. I'll show you in the next few slides how we made our trade-offs and what we were willing to accept. And here it is. This is the terrible slide of terribleness. I promise there's only one of those. All these nice little underlined things are links with why it says that and why it's a good or a bad thing for us. Quick voiceover for this one. Anybody who's been around for a while may notice that Kestrel isn't on the list. It was Twitter's big touted queuing system. Twitter doesn't really actively maintain it anymore, which is a shame. It was a cool idea, but that's why that one didn't make the list. Like I mentioned, we are in AWS, so I would be amiss to not look at the things that are hosted for us, which is Kinesis and SQS. And then, of course, RabbitMQ is probably like the leading open source one next to Kafka. Kinesis, the biggest downside there is that the clients need to be really, really smart. Goes hand in hand with Dynamo. After Sunday, I should have actually probably added one more concern on that. It says it needs Dynamo to actually work. But you need Amazon's blessed clients to really get the most out of it. And those blessed clients are right now in Java, .NET, Ruby, and Python. So if you like to program in another language and interact with the system, you're on your own, and you better duplicate that logic in the same way that the blessed libraries did. So a bit of a big drawback for us because we want lots and lots of system ingest and not just things written in those 4 languages. For SQS, the maximum payload, it's a bit of a challenge, 64 KB. I don't want to particularly be limited by that. I don't know how big our log lines are going to be or how big certain messages are going to be. To put that artificial cap in early felt a little scary. It's also 50 cents per million, which doesn't sound like a lot until you get a good chunk of the world's traffic, or at least a copy of the world's traffic. And then you're talking thousands, 10 thousands of dollars a day just running SQS, which is a little silly. Going down RabbitMQ, everything looks actually really, really cool. The ecosystem is fantastic, but they do have one thing that is tremendously concerning, and that's poor partition tolerance. They're very good about that. They document it very well. The edge cases are very, very clear. You know exactly what you're getting yourself into. But one of the very strong recommendations is make sure your network is stable, control your network. The network shouldn't go down, the network, the network, the network. And did I mention we run everything in AWS? So it's a little harder for us to guarantee that. But together with that, if the network is so important, that means that if you're in 2 data centers or in 2 physical locations, even if you control the network, you're probably not going to control that pipe between those 2 locations, and somebody with a backhoe is going to come by and mess your things up. So that was a really big concern for us. And then Kafka, there's a few things, a few shortcomings for sure. There's lots of metrics available, but they need some code. A lot of the management is CLI tools. It's kind of so-so, and it relies on Zookeeper. 0.9, which is the upcoming release of Kafka, is moving away from Zookeeper for good reasons, but scaling Zookeeper is actually a lot harder than scaling Kafka is. To the bottom right, there's 2 little links that I encourage you to go and check out. There's a gentleman called Kyle Kingsbury, and he wrote a tool called Jepsen, named after Carly Rae Jepsen. that helps you find the edge cases of a lot of distributed systems. So if you have a particular workload, a particular thing that is particularly interesting to you, you can configure Jepsen to test that use case for you and see how the distributed systems fail, because they will. They just all fail slightly differently. And he's done an excellent blog series around that as well called Call Me Maybe. And you should definitely go check that one out and read about your favorite system. All right, let's go here. We'll start with the simple stuff. It's the hello world of Kafka. Most tools come with a how to get stuff set up, which is all great. Let's just cover the basics real quick and a few little things to watch out for. And then we'll go to the advanced stuff. Terminology in Kafka, they say topics. What they mean is that's a queue for a specific set of messages. They've got a name, a replication factor, and a retention policy. That's the three things that you put in. What's the thing called? How long do I keep it around, and how many copies of it do I want? Producers create messages to topics. Consumers consume messages from topics. And you can have groups of consumers that all keep in sync about what they process, and that's how you scale processing. That's basically it. The design is very specifically for spinning disks. So they've optimized write-ahead logs and stuff like that. Spinning disks in Amazon have very unpredictable latency if you use ephemeral drives. We've been bitten by that many times before. Back in the day when we couldn't get SSDs, we had a handful of systems that we use RAMFS very specifically to take the spikiness out of spinning disks, because you think it's your spinning disk, except you're spinning it, you're sharing it with 10 other people, so the needle moves, then jumps over here to help the other person and back again. SSDs, however, help a lot, and we didn't find any problems running on the ephemeral SSD storage, and it avoids the very, very pricey EBS provision IOPS, which is a great way to give Amazon lots of money, but not very good for your bottom line. On the bottom right, there is a fantastic article written by Jay Krebs, who's the author of Kafka, that goes into every one of their edge case failure scenarios. There's a few. You should be aware of them. Too long to get into here, but it's the best rendition I found of that. All right. As the slide says, the default is at least once delivery. If you want at most once delivery, you're going to have to build some client logic for it. And I think everybody here knows that exactly once delivery is a myth, so that's not going to happen. Zookeeper, right. Zookeeper is an application for maintaining state for distributed systems. It works on the standard quorum model, which means if you have more than half plus one available, it can make a good decision. From its own documentation, it says, you will want to have a supervisory process that manages each of your Zookeeper server processes. Exhibitor, which is open source by Netflix, is probably the best companion process for that. I suggest if you are running Zookeeper, run it together with Exhibitor, and you get your nanny process. It also comes with a nice little UI to actually manage Zookeeper, and you get away from all the pesky little client tools. All right. A handful of things to remember when you're setting up your first Kafka cluster. Whatever the partition number is that you decide, we picked 6. 6 is a pretty good number to start with. It should be the same size as your initial cluster. That way you have one partition of data on one node. That's your ideal scenario. You can grow it as much as you want, but keep that in mind. However many partitions you want, that should be your initial cluster size. Replication factor of 3, it's a sweet spot we find because 1 failure still allows for quorum, and 2 failures allows for some data recovery, usually most data recovery. So 3 is a pretty good number to go by. And the most annoying one is that every Kafka server process needs to have a unique ID. Unique IDs are hard because now you need to have some sort of central system that makes sure your IDs are unique. So what we did is we took the IP address and we converted it to base 10. IP addresses are unique within our environment, so we might as well use that. So it's just a clever little hack so you don't have to have a central system to assign unique IDs to the thing. And so here's the bonus tip. Kafka's performance and its lookback windows are mostly dictated by disk speed and disk size, respectively. So if you can just get a bunch of big SSDs in a single node, it's going to go a long way. If you're in Amazon, look at i2s or high 1s. All right, let's get to the slightly more interesting stuff. Hello World is all fine and dandy, but it doesn't actually get any data into Kafka. They're not very good about generally documenting how your workflow gets into Kafka. So let's try to answer those messages. With a discovery use case, you probably have something like, I get a web request, and my web request has a log, and then mumble, 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 and then it ends up in Kafka. So what we need to solve for is I have an individual log line. I want to convert that to a message format that Kafka understands, and then deliver to the right topic so I can later consume it. So let's go figure out what we can do there. I'm assuming that in most cases, your web requests are served through some sort of web server, Apache, Nginx, Lydie, whatever you like. Any one of those can, of course, be configured to capture the logs. In the examples, I'll use Apache, but Nginx and OmniTI have exactly the same type of feature, so you can do it there too. As a quick aside, the Apache image that you see there is from an ApacheCon t-shirt from 2003. One of my friends owns it. And I really wanted to use it for the presentation, and I Googled so much, and I couldn't find it. So I contacted my friend. It's like, do you still have the t-shirt, and can you take a picture? And he said, sure, here you go. It's like, why can't I find it online? He's like, well, McDonald's didn't really appreciate the joke. So there you go. Apache has a standard log format, but you could, of course, specify your own. I'm sure we've all done that in the past. Since we intend to process this data, why not just optimize our log line directly for consumption? Apache has a standard log format, but it still means you have to parse it at the other end. So what we do is we log directly to JSON. Now, I say to JSON. If there's any double quotes or single quotes inside of the strings that you're logging, of course, you're going to break your JSON thing, but URL encoding usually solves that. So in this case, we capture the timestamp as TS, the path that was requested, the response time in microseconds, the time that it took to serve the request, that's RT, and then the version. We version all of our log lines because once we change our mind, we have a log file with a version in it so we can adapt the parsers. Oh, I found version 1, I have these fields. Oh, I found version 2, now I use these fields. So we can backwards compatibly process all of our data. So using this format, you can quickly correlate all these different things, and now you have a single line of JSON per HTTP request. Great. The second part is, why would I write that to disk? Remember, I want to get it in Kafka. I don't want to write it on a disk. So why write it to a disk only to read it from a disk? Now I'm spending disk I/O twice, and disk I/O is precious. So what we do is we open up a custom log pipe to Netcat. Netcat is like the best tool in the world. The nice part here is you don't need additional process monitoring because Apache will do that for you. You use UDP, which is fire and forget, which means that Apache isn't blocking while you're logging, which it does on disks because it has to write and then flush. And the nice part is localhost UDP is very, very reliable. It stays in kernel, so the kernel knows if it did or didn't arrive, and it does all kinds of cleverness. The -j flag, anybody know what the -j flag does, just out of curiosity? See? Same here. It's an undocumented flag, but it's part of OpenBSD's Netcat. It's jumbo frames. If your log lines per line are more than 1K, this lets you do big frames. So caveat here, you do need OpenBSD's Netcat, not Linux's Netcat. There's a package for it. You can just go grab it. But again, OpenBSD Netcat. Right. So now we have log lines that we can stream to some process. Awesome. Next tab. You need to transport them off your box somehow. Ideally, you want to do that in some way that is really, really low overhead, right? Because you're going to be streaming all these log lines. You've tuned your web service to take as many requests as possible. The last thing you want is this massive, massive process that all it takes is some data over here and shuffles it over there and eating up half your CPU. So rather than embedding a full-on Kafka client on the box itself, which is a little memory hungry and needs to talk to Zookeeper a lot to get its state, we try to look for something that was very low overhead and just shuffles bytes around. There's a few important features that you want to look at for anything that's a transport option. One, back pressure. There's always going to be a time where you can't get it off the box fast enough, or your network is slow, or CPU, something. So you don't want something that just takes it and hands it off and drops it in the middle if it can't. The next one is remotes do go away, especially in Amazon. We have box failures all the time, so we wanted to very cleverly switch from one remote to another when it goes away, but back again when it comes back up. And a feature we really like is both fan-out and consolidation of streams, very specifically fan-out. So when we do a major upgrade of Kafka, we'll do a secondary Kafka cluster. We take our transport layer and say, send it to 2 places. Then when we're convinced with place number 2 being good, we remove place number 1. If you don't have that, you do a hard switch over. You're going to lose some data. Some of them are going to be on the old. Some of them are going to be on the new. And like I mentioned, low overhead. So at Crux, we use piped. It's open sourced. We did it back in the day. When we wrote that, there weren't really any other big open source systems available. None of them are really mature. So we kicked a tire on a few. It was kind of so-so. So we optimized for our use case, which was UDP to TCP transport with all the features there. For us, it still solves this use case better than anything we found out there. But when it comes to community adoption, Heka, FluentD, and Flume are definitely the top 3. I would encourage you to definitely check them out and pick the one that best suits you. If you are going to go with piped, this is kind of what it looks like. We listen on UDP and TCP port 9002, the admin interface on 9003, because then we know what the hell's going on. Very important. We love us some statsd, so we send stats on everything that's going on directly to statsd, and then we just give it a list of servers to listen to. And so if everything's well, it's going to go to listener 1. Listener 1 goes away, it goes to listener number 2. Listener 2 goes away, it goes to number 3. 1 comes back, it goes back to 1. The fan out would simply be adding another array of listeners right after that. Here's what admin looks like. If you run the stats command there, it'll tell you how many connections you've had, how many messages it's sent, how long it's been idle, how long it's been up, yada, yada, yada. And also what the state is of your various remote listeners. We use that for monitoring. So I can see from all the places which remotes are up and which ones are down. For us, the main consideration to keep using piped right now is the performance profile. It's written in Node, so it has some quirks, but it's pretty fast and reliable for us. We get about 85,000 QPS out of it on a single CPU on a C1 medium in AWS. When we benchmark our syslog, which was our fallback at that point, we didn't get it over 10K. So, 8x performance improvement for your own tool goes pretty far. All right. So now we have new line delimited content, and we can stream it off of a machine. But we still need a system that ingests that stream and makes Kafka messages out of it, right? Because Kafka has its own little proprietary binary protocol. You still have to do the conversion. We wrote a thing called Kafka Stream Listener. It does what it says on the tin, and it's kind of the Swiss Army knife that we use to do that. Because it operates on an incoming stream of new line delimited data, that means creating clients for it is really, really trivial. If you remember back to the Kinesis comparison, we said it only supports 4 different sets of clients in 4 different languages. In this case, we even have some bash scripts that can just do something pipe netcat, and there it goes. So even the most rudimentary scripts that we have, maybe at the end of etc init script and so on, we can add things to it, and we have Kafka compatibility. So that's why we like Stream Listener so much. Here's hopefully how that looks. You create a port to topic mapping. So you say port 9001 in this case goes to topic 1. If that also needs to go to topic 7, for example, you do topic 1, comma, topic 7. Port 9002 to topic 2, and so on and so forth. So just keep all these ports open. Message comes in that goes on that topic. It again comes with an admin interface because we like us some admin interfaces. And it also comes with a heartbeat topic. Making sure that whatever is ingesting your stream is up and at the cadence that it's running is pretty important. So this is just one more way to verify the full cycle. I can speak to Kafka, I can consume my own heartbeat, I can speak to Kafka, I can consume my own heartbeat. Let's see, what else is important here? There's lots and lots of tunables. Part of our tool set exposes all of the Kafka tunables as well as part of command line options. So if there's something you want to do about ACK or retry windows or whatnot, it's a specific tunable you get there. Stream Listener, like all of our Java code, is built on top of our Crux Java standard library, linked from the bottom there. And it also adds a lot of logging and a lot of stats and a lot of CLI functionality. So with the -- stats argument, you get very detailed statsd type stats on everything it's doing. The amount of messages in on any given topic, delays, retries, yada, yada, yada. This is the output of our status command. We use that for monitoring. So state OK means everything is dandy. It'll show you the topics that it's listening on and kind of what the processing time is in nanoseconds, and then how many we've had and what the general rates are. It's a good way for us to check out the health of a system. And again, this all goes into statsd, so we have graphs all over the place that show us these things. If you haven't heard of the JQ little utility yet, it's probably the best thing ever for JSON. It's a little command line tool that lets you query, process, and introspect JSON. So we almost have all of our data in JSON, and it's pipe JQ, do a thing. And that's how we do it. All right, 3 things to keep in mind when you're writing a consumer or setting up when you're setting up a producer. Compression codecs. There's a lot of performance increase you get from using compression. It's definitely recommended, but there's a little catch. Compression is end-to-end, so it's not producer to Kafka, it's producer to Kafka to consumer. So the whole pipeline needs to speak the same compression codec. Snappy is by far the most performant for us, so I suggest that you use it if you can, but make sure, again, that your whole chain speaks the same compression codec. There's 2 types of producer types, sync and async. We haven't found any real benefit of using sync, but there is a real big drawback. It's a lot and a lot slower. So if you want to get your throughput up, you definitely have to set it to async. And then for ACKs, you have 3 choices. There is 0, no ACK needed. That's basically UDP, but now it's fire and forget over a wire, so you don't know if it ever got there. Generally a bad idea. You can set it to 1, which means that the leader confirms that the message was gotten there, so that one of the 3 replicas has it. And then there's -1, which makes sure that all the replicas got it. If you're paranoid, set it to -1, but it does come at a pretty hefty performance penalty at that point. So we use 1. We accept the fact that if we sent a message, the leader acted, but the leader went down before it replicated, we lose that 1 message. Back to our earlier thing, there's no morphine involved and we're not investing money. So that's kind of your tunable there, 1 or -1. There's a few other things that you should keep in mind, specifically your message batch size and the max send interval according to your preferences. We use 2000 for message batches. It's a nice thing between not waiting too long and getting good throughput, and 500 milliseconds for the send interval. So that means that no longer than 500 milliseconds will we wait to send the next batch. So whatever comes first, 2000 or 500 milliseconds. Great. So now we have a whole bunch of data in Kafka. Now let's talk about what it takes to get that data back out of Kafka again. Kafka is a pretty rich ecosystem of tools and code that it integrates with, and they're all linked from the bottom right there. But I'd like to focus on a handful of tools that are particularly suited for those use cases that I described earlier. So we have a web server, request logs goes in. I told you about how to get the logs, transport, and into Kafka. And then, again, mumble, 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 and now our business logic comes out. So let's look at the tools that we use for those 3 use cases. For search and discovery, ELK, EOK, Elasticsearch, Logstash, Kibana. Is there anybody not familiar with ELK? Yeah, they've done a good job marketing. I figured as much. Logstash has plugins for lots of inputs, lots of outputs. It's a really, really cool tool. And it includes Kafka. It's supported by Elastic, so that's awesome. You have some basic processing as well. We try to solve it all on the format to begin with, because every CPU cycle that I spend over here munging the message that I could have just written correctly over there is a silly CPU cycle wasted. But Logstash does have a few quirks when it comes to working with Kafka, so I quickly wanted to go through that configuration with you if you're also setting up Logstash. This is part 1 of the configuration, which is the input for Kafka. There's a few things you definitely want to set. Auto offset reset. You have 2 choices, smallest or largest. If you set it to smallest, you assure at least one's delivery. That means if Logstash goes away and it comes back up again and it can't find its exact state for network reasons or whatnot, it has 2 choices. Give me the oldest thing that you have, Kafka, or give me the newest thing that you have. We'd rather have a message twice than not at all, so offset smallest. The group ID has to be a unique name for all of your Logstashes to share. So if you have 5 Logstash or 10 Logstash servers, make sure they have the same group ID, because then they can multiplex their processing. If they all have unique IDs themselves, you're going to have, if you have 5 Logstash servers, you're going to have the message at least 5 times. You have 10 Logstash servers, you have the message at least 10 times. Whitelist, you best be explicit. Otherwise, Logstash is going to be really, really helpful, and every new topic you add to Kafka automatically gets added to Logstash and then automatically gets sent to Elasticsearch. You probably don't want that. So just list the ones that you want. And the most important one is decorate events. You need that for all the metadata that you'll want to set up your indexes and your rules automatically. It basically adds a Kafka key with a whole bunch of stuff on top of it, and you have to set that key to get it. Filter. You need that, unfortunately, because the type key is special in Logstash. And the type key is as is passed to Elasticsearch as the type of document you're sending. And you probably want to have something that is Kafka specific. The documents that you find on topic number 1 are probably different from the type of documents you find on topic number 2. So we set the type to Kafka : indicating it's coming from Kafka, to whatever the topic name is. Then in Elasticsearch, we can set up templates and rules and so on, saying this is how you treat topic number 1, this is how you treat topic number 2. And the rename thing is just a quirk on Logstash, because they realize that once you have the typeset, you should probably not change it, so you can only overwrite it. So you have to do that. And then the second part is to get it into Elasticsearch. The host list doesn't have to be an exhaustive host of Elasticsearch nodes, but it does have to, at least one of them has to be up, because it will connect to that one and then find out who all the other Elasticsearch hosts are. So consider them bootstrap hosts. It doesn't have to be exhaustive. The cluster name has to match the name of the Elasticsearch cluster. It's a failsafe that Elasticsearch puts in, so you're not accidentally connecting to prod or dev or whatnot. The default name of the Elasticsearch cluster is Elasticsearch, so you can pick any name you want. I suggest do not pick Elasticsearch. And then importantly, the index. We prefix the index by the consumer group. In this case, it's a Logstash cluster, because there might be other things indexing the thing with other rules, and so you don't want those to clash. And then we set it to the topic, again, because topic 1 probably has different documents than topic 2. And then lastly, we set it to a date stamp of year, month, day, hour. Default is daily, but it's a lot harder to control your outputs that way in your disk I/O, so when compressions come along, especially if you have a lot of stuff, right? So you have like, oh, lots of data, lots of data, lots of data, drop, lots of data, drop. So we found a much more consistent pattern by doing it hourly, and it lets us much more granularly control the life cycle of indexes as well. Maybe some of them we want to keep for 12 hours or 36 hours rather than 1 day or 2 days. And the bonuses here use the statsd output. Logstash is hard to monitor, unfortunately. It doesn't really have good plugins or good ways to know what's going on. So all of our stuff emits stats per topic into statsd, and we have our monitoring and alerting set up to that to make sure that happens. And the thing that I don't have in here is we have another output, which is a Logstash heartbeat into Kafka. So every 10 seconds or 60 seconds, I forget right now, it emits a little message to a Kafka topic. So it's another way that we at least know that Logstash isn't hung. All right. Now, for a lot of your topics, you'll probably be creating either standalone programs or you'll be embedding processing logic in some other application you have. If you're a Java shop, I very much recommend that you use our Crux Kafka standard library. It's basically a layer on top of Kafka's Java libraries and includes things like a very extensive logging, so you know exactly what's going on with your topic, when you can reconnect, what's there, what's not there. Lots of stats around processing times, what's accessible, what's not. And it exposes all the Kafka tunable CLI options to your operators. So when they find that network lag has increased and they want to up the refresh interval, rather than having to recompile your code or change a config file, it's a -- Kafka property. So this is how we make friends with our developers. We have a standard library in Java, say just build all your Kafka tooling on this, and it exposes all the knobs and dials for us, the operator, to say, I want the stats for this, you need to connect to a different Zookeeper host, and by the way, this is the timeouts that we're okay with. All other tools I'll be showing you are built on top of that library as well. Again, it's linked from the bottom right, and so we use it for all of our internal processing code, which is billions and billions of things every day. So hopefully it'll work for you as well. Here's a small demo program. Again, a full one is linked. I was really proud of myself because I'm not a Java head, but I know that writing short Java code is really, really hard. And so to get an actual working demo program on a single line, I fudged the import statements, okay, but to get a working demo program on a single slide, I was pretty pleased with myself there. So at the top, that's the invocation. So you would just run it with -- topic threads, topic 1, 5, topic threads, topic 2. The -5 is the amount of threads. By default, we'll give you 1 worker thread, but maybe you have a heavy topic, you want to process a lot. Again, us operators can say, oh, that topic has a lot of data on it. I'll give you more resources. Then we add all the Kafka command line arguments there. That's like those first 4 lines of setting up the standard lib. Set up the handler, and then at the bottom, you get the business logic. And that's where you would hook in your specific thing. Like you get a message, you analyze it, you do a thing, you update a thing. So this is the shortest demo app that we can produce. And there's lots of examples in the open source code. Some people prefer a processing framework over just some Java code that they write themselves, and not everything goes into Elasticsearch. I think a lot of people are familiar with MapReduce and Hadoop and kind of how that works. There's 2 frameworks like it, which is Spark Streaming and Apache Storm, which kind of work like Hadoop if we fudge a little bit, but it's very specifically for stream processing rather than for batch processing. So if you very much care about a workflow, like first I do this thing with a message, and then I do this thing with a message, and then I do this thing with a message, these systems are probably for you. They have their different strong points and weak points. But these are the top 2 leaders right now in the open source community, so go check them out and see which one works best for you. Just like with the other things, there's a few very important things to notice when you're setting up your consumers. There's a setting called fetch message max bytes. That is not dynamically determined. And you have to make sure that the biggest message that you are sending as your producer is smaller than this setting. Otherwise, you'll get a chopped off message. Kafka's not smart enough to go like, hang on a minute, buddy, that message is actually larger than what you told me to fetch. Now, by default, it's set to 1 megabyte, so you don't often hit this, but you want to be sure. Otherwise, you're going to get a lot of corrupted messages and a lot of errors. So just go double check that whatever the max byte size is enough for you. Conversely, if you know it's much smaller, you can get small optimizations out of setting that a little smaller. There's an interesting setting called rebalance max retries. Whenever a new consumer joins the Kafka pool or a new server joins the Kafka pool, all the clients get notified basically and says, hey, we may have to rebalance a little bit. And you're like, okay, no problem. And they go ask Zookeeper about the new state of the world and be like, okay, I'm going to do this, I'm going to go do that. As a, let's call it feature of Kafka, when another consumer joins while that rebalance is going on, the rebalance fails. It says, oh, try again. After 4 times, by default, it stops. I've tried 4 times, I don't know what to do. So if you have a highly dynamic system, maybe if you're using something like Storm or Spark Streaming, where resources are allocated as necessary, or maybe you're in an Amazon world where you spin up and down nodes all the time, or maybe you're doing a rolling restart across your cluster and all the consumers go down for a few seconds and then come back up again, 4 is not a very big number. And so we found Kafka processes just stopping because the rebalance failed very often. We've not found any downside whatsoever to setting that to a larger number. So just set max retries to something large and you'll be fine. The offset reset. Here's, as I mentioned for Logstash, you basically have 2 choices. One is smallest, the other is largest. Depending on how painful it is for you to get a message twice, make your decision. We generally find that smallest is best because of how message delivery works anyway. You are likely to get the same message twice at some point. The higher the amount of messages you send, the more likely it is that you're going to get a message twice. So we, back to constraints and embracing constraints, we just said, okay, that's just going to happen. So we'll set the auto offset reset to smallest. This will definitely trigger in 2 cases. One, where the Zookeeper state is lost. And remember, there was some dependency on Zookeeper. It's a little fragile at times, so that state sometimes is lost. So what do you default to? We say smallest. And the other one is if you have a highly volatile queue, you might be moving through it so quickly that by the time that consumer comes back up again, the offset that it has is past the end of the queue. And then the question is, well, what do you do? And we say, go to the oldest thing you have rather than skipping all the stuff that came in ever since and go to the newest. So my recommendation, auto offset reset to smallest. Right. So now you have a growing infrastructure, you have a growing footprint, and you're unlikely to only have a single data center. In fact, who is here operating in just one data center? Exactly 0 people. Oh, 1 person, 2 people, sorry, 2 people. Those were small hands, by the way. Like, they weren't like, yeah, and they're like, so you have 2 choices when you go to a second data center. Choice number 1, duplicate your entire deployment across your 2nd, 3rd, 4th, 5th data center. Just make them autonomous little units. Or you can treat your other data center as satellite data centers and replicate your data to a central data center. The upside of the first choice, obviously, is that all data centers are independent, which is really, really good. But that also means that your pattern inherently says that access across data centers becomes harder. We find we have a lot of metadata that we need to move around. So if we had to move that metadata to all of our edges, getting that in sync is actually harder than replicating into our central data center. The upside for the centralized one is that you can optimize for economies of scale. I promise you it's the only buzzword I'm going to use all presentation, but you can optimize for the economies of scale, which is what we did. So we have our biggest zone is US East 1, and we replicate in there. So how does that work? It's the same thing as before. Now your web server is just based in a different data center, and then something mumble, mumble, mumble happens, and you want it to come to the Kafka in your main data center. You could run a direct stream listener connection. So you just do the same thing as we did before, Apache, log format, netcat, piped to stream listener, and then have your stream listener connect across either the ocean or across the continent. It would work, but you would probably drop messages and you wouldn't have a lot of support for back pressure. Because once there's a network partition or an outage, you have nowhere to go. Now, if that's just for a few seconds, you probably can do it in RAM, but if you have a high volume, it's not going to work. So you can compensate for this by running a much smaller Kafka installation in the satellite data center. Both in terms of CPU as well as in disk, you can need much less capacity. In fact, we run it, I think, on 6 C3 largest per remote data center, which are basically, if you have a MacBook Air, that is more powerful than a C3 large. You need less CPU because the only process reading from all the topics is the thing replicating across to the other data center. So it's much less work to do all the calculations. And you need much smaller disks because you're not trying to do the full queue retention. You're trying to compensate for the amount of messages that you may have to back up before the connection comes back. And that directly relates to the amount of time that you can compensate for downtime. And your operators will really like that because if the connection goes down, do you want to be paged right away or maybe after 2 hours if it's still not back? I prefer after 2 hours. So we aim for about 6 hours of retention on those boxes, and it works out pretty well. We haven't seen anything more than a few minutes. Just something to keep in mind is that you not only have to have the retention period, when you play catch up, you're probably going to be a little bit slower because you have to go through a backlog. So it's both the time that you're down plus the time for recovery. So we wrote our own version of a mirror maker. Kafka comes with one. A mirror maker in the Kafka world is in essence just a consumer and a producer bundled in the exact same application. What it does is like takes message off topic locally, puts it on topic remotely, acts the message locally, repeat. Our mirror maker is a more advanced version of the Kafka one, and we bundle, it's a more advanced version that is already bundled with Kafka itself. Importantly, it does the following things. It has enhanced logging. The one that's bundled has almost no useful logging for us. And it's particularly interesting when you go like, hey, the replication is running behind. What's going on? Like you don't need the logging in a sunny day scenario, but as we all know, it's not always sunny day scenarios. We emit lots and lots of stats because that's just how we both visualize and understand how our systems work, and that's what our monitoring is hooked up to. So any tool that we get that doesn't emit stats, it's very hard for us to get a really good insight on what's going on. Poking it every 60 seconds just gives you a snapshot of the moment that you poke at it, which is not as useful. And then we have that __ status endpoint that I showed you earlier for the other tools here as well, so we can see what's going on with the mirror maker at that point. Very importantly is our version supports SSH tunnels by mapping local ports to remote endpoints. Zookeeper will tell you about the remote endpoint you need to hit, and we know how to do a little mapping and route that traffic over a tunnel. That's kind of crucial if you don't have a VPN. We don't have a global VPN, so your alternative is to send those messages plain text, hence this. Here's kind of what that looks like. So just like the stream listener, you hit the status endpoint, it'll tell you everything is fine, it'll tell you what topics it's mirroring, and how many it's done, and kind of what the process rate for that is. There is currently no topic lag in this output, as you might notice, and I'll get to that in just a moment. So again, for mirroring, there's a few key things to keep in mind. Log retention. Like I said, this is the amount of downtime plus recovery time that you need between your data centers. Once the connection comes back up, you do have to clear that backlog, and it'll probably take some additional time. Between the EU and US, which is the most volatile connection that we see, we use 6 hours, and we've been more than fine every time. Like I mentioned, Kafka is a plain text protocol, and you need to somehow encrypt that. Configure a VPN, it's actually what you should be doing, but for those of you that don't have a global VPN, actually, who doesn't have a global VPN? Okay, so you and me, we need to use SSH tunnels, and everybody else is way cooler than we will ever be. And then there's topic lag. Topic lag means that your remote data center isn't copying the data to the central data center at the rate it's coming in, or at the rate that it has come in. So that's probably the most crucial thing that you'd need to be looking at. So even if you get, I don't know, usually 10,000 QPS, but you get a spike of 50,000 QPS for a couple of minutes, and your replication can only do 10,000 QPS, you're always going to be that chunk behind. And it's very hard to see on graphs unless you know exactly what the topic lag is. And I'll show you in a moment how we actually monitor that. At the bottom right, there's a great presentation by an SRE from LinkedIn who works on Kafka and Samza and that tool set. And that's probably more than you ever wanted to know about how aggregation works inside of Kafka and how replication works and how it breaks. So once you do that multi-data center setup, definitely go follow that presentation and dot all the I's and cross the T's for that one. All right. We just introduced lots of new moving parts to get this whole replication thing set up, that whole ingestion pipeline set up. Not all of them come with management or stats out of the box. We try to put as many in our tools as we can. But in order to really trust that real-time data pipeline, you're going to have to verify that it's behaving the way that you expect it to. So even though we put some of our stuff in our tools, there's still some more things that you can do. So let's expand that little diagram with some tools and code to get there. Number one is an app called Kafka Manager. The folks at Yahoo have graciously open sourced this. It's probably the easiest way to manage and visualize your Kafka clusters. It does three things, basically. You can manage clusters, you can create new topics, and you can do very basic maintenance levels. Kafka is a really stable bit of software, so usually you just have to go in and make a few little decisions when it's not quite sure what the best thing to do default is, and Kafka Manager exposes that. You set it up, you do a little bit of config via the UI. You do have to open up your Zookeeper client nodes for it because that's how it knows about the state of the system. So that backend application needs to have access to Zookeeper. And unfortunately, it doesn't have any authentication. So you do have to front it either with like Apache Basic Auth or put it behind a VPN or something similar like that. But definitely check it out. It's an incredibly useful tool. And this is the bit about Kafka that makes me sad. This is a little quote from the doc. The easiest way, I emphasize, the easiest way to see the available metrics is to fire up JConsole and point it at a running Kafka client or server. This will let you browse all metrics with JMX for certain definitions of easy. So we figured there must be an easier way, and I definitely don't sit around with JConsole all day trying to figure out where my Kafka clients are and then poking them and seeing what's going on. So a little bit further down it says, Kafka uses Yammer metrics for metrics reporting in both the server and the client. This can be configured to report stats using pluggable stats reporters to hook up to your monitoring system. It's like, great, that's what we actually want to do. So the picture you see there is our actual Kafka dashboard. And I'm going to show you how we kind of get all that data out. Our Kafka tools are based on, a quick side note here, our Kafka tools are based on 0.8.1. 0.8.2 came out a little while. In 0.8.1, neither producer nor consumer libraries have access to some of the fundamental Kafka server stats. There's no particular reason for it, they just don't expose it. In the newer one, 0.8.2, the producer has added stats, and 0.8.3, the consumer has added stats. So we'll be updating our code as we go along, but in the meantime, the Kafka server does have all the stats, and so you can add that reporter jar in, which is what this little code snippet shows you. So when you have the Kafka configuration file, add these couple of lines there, and drop in our reporter jar, and you get the same graphs and reports that we did. Kafka internally already does all the rollups and averages, which is why we send it directly to Graphite rather than sending it to StatsD, because StatsD does rollups and averages, and then you get rolled up averages of averages, and then those numbers mean nothing. I think if Theo were on stage, he would yell at you for about 2 minutes why that math doesn't make any sense. And this is topic lag. This is the most important thing that we can possibly be monitoring. So topic lag is the crucial thing because if that pattern deviates from that normal like little sinus thing, you're lagging behind, and there's no other way of knowing it than watching this or looking at this graph. Like I said, this is an actual graph. You notice that it's slightly spiky. That's because the clients log their offset every 60 seconds. So take a snapshot, and 60 seconds later you get a number, 60 seconds later you get a number. So it does that little jaggedness, and that's fine. And I think you can also really see our seasonal pattern there, especially if you look at the green line. So you see that I took this screenshot on Monday because it's like 4 bigger spikes and then 2 flat spikes and then 1 big spike. There you go. All right. So there you have it. That's basically all the bits, how it fits together. You got vanilla Kafka, you get an ingest pipeline, you get processing pipeline, you get replication, and then the inside the management tools. And who can resist adding Hannibal Smith and saying that you just love it when a plan comes together? All right, so here is the final picture. And I think the last slide is, yeah, questions. There we go. Want to leave ample time for questions, so now's your chance. Sir?
Do you consider Logstash on the ingest side of pulling log off servers to be Kafka?
Have I considered using Logstash as the ingest side? Yes. Logstash, as long as you don't have to process data, is incredibly fast. As soon as you have to do any type of alterations, it gets slower and slower and slower. And the overhead of running it is basically non-zero, plus it's another process and another connection to manage. So our 2 main ingest points are syslog and Apache. So both of them, I could do an immediate UDP hookup to the same piped instance, which would then go off to Kafka. So Logstash is absolutely a viable thing, but understand it comes with a little bit of extra overhead. And if you have to do any processing, it gets very, very expensive very, very fast. Any other questions? Sir?
Syslog NG, which basically is about to come with a Kafka plugin. I mean, what problems do you see on syslog side from an ingestion standpoint? Like, do you have any performance data, like how much of messages can pass through it without issues?
So make sure I get the question right. Are there any concerns about using syslog, syslog-ng, or rsyslog? I'll just throw that one in terms of performance and how many messages can pass through. There's two specific challenges. Syslog, as it comes out of the box, I think we all know is good for a couple of messages every minute. Let's say second. Let's give them the benefit of the doubt. Syslog-ng and rsyslog are much more performant. We like rsyslog because it is, or at least when we did it, more performant than syslog-ng. Syslog-ng seems to be more fully featured, and they've put a lot of effort into performance. I'm going to answer it mostly from rsyslog because I know exactly the constraints there. One is rsyslog is really hard to introspect. I don't know what your backlog is. It has two methods of handling backlog. One is in memory. You tell it, use this much memory, but it won't tell you how much it's using, how far it's behind. It'll just try to do the right thing. And the next one is on disk. But it's, again, it's a proprietary format, and so it'll just use a blob of disk space, and you don't know how far it is behind or not. So I don't have a good insight in what it's doing. We're nuts about stats. So that's kind of where rsyslog fell over. The second part is we benchmarked it as much as we could and only got to about 10K QPS for a single core on a small machine, whereas we got 80K QPS from our own internal tooling. We like lots of small little machines because in Amazon they drop like flies, and so if I have big machines dropping off, I need many more big machines to compensate, because if there's a small machine that drops off, I need less machines to compensate. So that was kind of our trade-off. So the visibility and the raw QPS. If your QPS numbers are lower and you already have good syslog integrations with stuff, there's technically nothing wrong with it. It's just insights we couldn't quite get and raw QPS. Does that answer your question?
Yes.
Cool. Any other questions? Sir.
And this is probably an implementation detail of message processing, but how do you collate multi-line logs, right? So let's say you have a trace that drops in at 1,000 lines, and you don't want to look at that individually as 1,000 lines, but seeing that together as a single message inside of Kafka.
Yeah, what do you do with multi-line stuff? We don't do it from Apache, so that's pretty straightforward. And it would be pretty easy to collapse multi-line by using URL encoding or something like that. Sorry, I didn't repeat the question. How do you deal properly with multi-line, especially for stack traces? And I'm hearing Java?
It could be Java or Rails or whatever.
Java, Rails, or whatever produces standard lots of stack traces. So we have two sets of inputs. One is Apache web service like that, and where I can control the full-on log format, and they are by design not multi-line because Unix likes it that way, because that's how pipes work. So they're already pretty accommodating for it. For programming languages, we have both. I showed you the Java standard library. We also have a Python standard library. Those are our two languages of choice. We basically have error handlers in there that say, when you get that error, you're not going to output it multi-line, but you're going to output it like JSON, and one of them is error, and we do the encoding. So our answer to that is make sure that all of your internal code is built on some sort of standard library, and log4j is infinitely customizable. So that's how you get around that. Any other questions?
I have a question.
Go ahead.
This is related to topic management, like the way that we have our message flow is all the messages come to syslog, and then from there on, basically hits the log stash, and where we basically decide on the topic and change the topic and put it back in the producer, like Kafka queue. Another set of log stash come and pick each of these. We have several groups, consumer groups, handling each of these topics.
For
Is there
redistribution.
any better way of doing this? Because what we are having is a single stream of syslog, but when we parse that with logstash and try to change the topics and put it in individual topics, and then another logstash comes and picks it up and transforms and indexes.
So the question is, if you have one big stream of syslog or something like it, you kind of have to parse the content to figure out what topic it should have gone on to begin with. So their solution right now is just dump everything on a generic topic, and then have something listen on that topic, and then decide what actually should have gone. But it seems pretty intensive. So there's a handful of things you can do there. One is syslog does support different facilities and different severities and also program names. And so our standard libraries that output to syslog basically override those and don't say, send everything to user sev warning. It's like, no. Use the facility that says this is meant for Kafka, which is one of the other user ones. And then we make sure that the program name isn't Python or something like that, but is an actual useful indicator. But that's, again, the same answer I gave to the gentleman before, is it does require you to have the right libraries installed or your own libraries installed so you can catch that early. Other than that, I think you're kind of on the right path. Processing has to happen somewhere. We try to do it as much in the client as we can because it avoids having to waste the CPU cycles to say, well, you already wrote it, but now I have to interpret what you wrote. Plus, that way I can make the developers or the people managing the code responsible. It's like, you want a topic for your stuff? Put that name here and it'll work, rather than go find the magic string somewhere in the stream. That's the best answer I have right now. Any other questions, maybe from that end? Sir? Question about back pressure, sure.
You have in your transport and correct string listener, Kafka goes down. What do you do with the back pressure? You just choose memory, or you just go to disk?
What do you do with the back pressure when Kafka goes down? At that point, you're basically hosed. That's it, right? So you set up your Kafka in such a way that ideally it doesn't go down. The way that we co-locate the stream listeners with Kafkas, they all have failovers to all the other Kafkas, but they prefer their local one, so they have health status and know how to fail over. Once Kafka actually goes away, the clients have a little bit of back pressure because the way we configure our stream listeners, and it's a tunable that I didn't expose here on the slides because it got kind of messy, is you have the choice by saying, if either my preferred Kafka or any of the Kafkas aren't available to me, stream listener, what do? Do I just accept messages and write them to a log file so you can later process it, or do I just shut myself off? And so depending on what your topology looks like and how you set up your preferences, you could say, if I can't reach Kafka, I'm just going to shut myself off. Back to our transport, piped will be like, OK, I can't reach you anymore because you can't reach Kafka, so I'll go to the next one. If they all go down, you have to make a decision somewhere in your topology. Can I drop messages, or do I dump a log somewhere and replay them later? So your real job is to configure Kafka in such a way that ideally it doesn't go down. If you're paranoid, run 2 Kafka clusters. 2 different versions, whatever you want to do. We actually, a thing that I didn't show you is we have a stream out of piped, so it's a different thing. And its only job is to go to a handful of big-ass boxes with fast drives, and all they do is log all the lines. So in case of a catastrophic failure, we can figure out when it went down and when it recovered, and we know all the lines that didn't make it. It's an annoying process, but at least we have something. So that's how we do it. Does that answer your question?
Yeah.
Cool. Any other questions? Sir?
For Kafka and Amazon, are you running, so if you're in US East, are you running all of your zookeepers Kafkas in one AZ inside of US East, so US East 1D, or are you sort of dancing with the devil and spreading zookeepers across multiple AZs, or what are you doing for that? Because
The question is, so you run, sorry, say that last part?
Network latency and zookeeper.
Network latency and zookeeper, exactly. So his question is, so you're in Amazon, do you run everything in one AZ? And he was already chuckling because he knows the answer. Or do you dance with the devil and spread zookeeper out over multiple AZs? Choosing your trade-off here, the answer is multiple AZs, because if all zookeepers go down, Kafka can't function. As you remember, I said one of the downsides of Kafka is that it is using zookeeper. Now, luckily, zookeeper is pretty good about, I mean, the whole thing is a Quora model, so its reconciliation model is pretty good, but network partitions, though, are a real thing. The guys behind Kafka have also realized that that is the most fragile part for them, and so they're doing their own whispery type of protocol like Cassandra does going forward. We'll see how well it does, but at least we have 2 options. So zookeeper, latency. We find that the biggest challenge with zookeeper is just lots and lots of connected clients. So the fewer clients you can connect, the better off you are, which is why we went from piped to stream listener rather than having native Kafka clients everywhere, because they would be pinging those zookeepers like crazy. And if they wouldn't be able to reach it, well, now what do? Surf stale? Might be right, might be wrong. So that's one way that we try to deal with that. And we do keep the Kafkas and the zookeepers very close to each other. So you wouldn't put, say, zookeeper in US East 1A and B, and then your Kafkas in C, D, and E. So at least make sure that there's a few Kafkas nearby, a bunch of zookeepers. That ups your odds of core. Luckily, we've been running this for quite some time. We haven't seen any catastrophic failures in zookeeper not being able to talk to each other, but we have been able to have so many connections to zookeeper that zookeeper became unacceptably slow. So that's what we've optimized for. Does that answer your question? Perfect. Do we still have time for more questions? Do I need to wrap up? I need to wrap up. So I'll be hanging out over here somewhere and later over lunch. Come find me, and thanks for listening.